So there's not much for you to do for this pre-lab. I would like you to read through the intro stuff, and there's a couple of pre-lab questions that we'll go through together. So you can read through. I think the stuff about the complex ion is pretty self-explanatory. Basically, in this equation, we're going to take iron 3 and thiocyanate, and they become what we call a complex ion. A complex ion has a metal with something else around it. So in this case, it's a negative thiocyanate ion. And you can read through the rest of that on your own. I want to talk a little bit about Beer's law. So Beer's law is one of the formulas that's on your formula sheet, and we'll be looking at it more closely in our post-lab stuff. But we can use this to figure out the concentration of different solutions, and then we can use that concentration to figure out K, which is what we're going to do in this lab. So we can kind of go through it. The capital A is absorption, which we're going to use a spectrophotometer to measure. The small a is a constant for a substance at each particular wavelength, so we can figure out what that is as we go through. B is going to be the cell path, so it's like the width of the cuvette that we're going to use. So we'll measure that, but it's going to be 0.75. And then C is the concentration, so it will be the molarity. So A, the little a, is a constant. And then the cell path is also a constant because we're going to use the same ones. So we can figure out what C is, concentration, based on the capital A that we see from the spectrophotometer. And then the rest of this is just a little bit about what, and then you can see the picture is missing on mine, but it's there for yours. A little bit about what the spectrophotometer does. There's a diagram in yours, and then just a little bit here. This is done for us. This little formula we're not going to need to use. This is done for us inside the spectrophotometer. What the spectrophotometer measures is the percent transmittance, but I click the program that we want absorbance versus concentration, so we can use Beer's law. So when I open up the spectrophotometer, which I'll calibrate for you and all of that, I click the program that does this automatically for us. Okay, so it takes the transmittance and it negative logs it, and so the number that it spits out for us is absorbance, which is just a much more useful number for us. So again, you can read through all of that text on your own, take any notes you think you need, anything like that. So that brings us to what the procedure is going to be. So we're going to make 2 different solutions. Each group will make 2 different solutions. We're going to start with everyone making the reference solution. And then each group is going to make a different test solution, and we're going to be able to use that information together to calculate our equilibrium constant. In the reference solution, you will notice that the concentrations of Fe3 plus and thiocyanate are vastly different. In the reference solution, our Fe3 plus is 0.2 molar. Our thiocyanate is 0.0002 molar. The reason for that is because we are kind of flooding with our excess reagent here, our Fe3 plus, so that we can automatically assume that all of the SCN minus gets put into that complex ion. Okay, so that way we can kind of, even though it's an equilibrium expression, if we flood it that way and make them totally different, we can use Le Chatelier's principle to kind of force the reaction to completion. Okay, so that's what we're trying to do there. If we make them so vastly different, we can favor the products so much that we can kind of assume it goes to completion. So that is what we are doing with the reference solution, and that's why we use different concentrations for those reference solutions. Okay, so equilibrium constant expression for the reaction shown in the introduction. Put this expression just above your rice box in the process the data section. So if you go to page 6, you have a rice box here. So they want you to write your equilibrium expression next to it. Okay, so your equilibrium, and you can write, whoops, KEQ, and we're going to be using concentration. So if you want to put concentration, either one of those is fine. And then our reaction, our equilibrium expression, is here. Okay, so we're going to take the concentration of the ion itself over the concentration of the thiocyanate and the iron ion. Now they're all 1-to-1, so we don't need to worry about any exponents or anything like that. Okay, so that's the expression that we'll use to figure out what Kc is. So that's pre-lab number 1. So pre-lab number 2, using the dilution equation, calculate the initial concentration of the thiocyanate and iron ion. Initial means after being mixed but before any reaction takes place. So it's like this imaginary situation in the reference solution, okay? Because of the stress discussion in Le Chatelier's principle at work as discussed in the previous section, the one-to-one stoichiometric relationship between reactants and products, we can assume that the initial SCN minus is nearly all used up. So that's what I was saying before. Okay, so put your calculated concentration for FeSCN2 plus here, and then we'll also put it, we have to put this number on our other table in page 6. So for this dilution equation, what they're trying to get at, and you'll see that we use little c's and little d's here, mostly because A and B is already in the Beer's law. So it's just not to get you confused. You can do any little subscript numbers there. So we're going to do that 2 times. So for the first one, what you're trying to do is figure out, okay, my molarity of iron that I started with was 0.200 molar. That's what the solution that I have made, or I had students make for me, is already. You are going to use 5 milliliters of that. And in the dilution equation, you can use any volume you want as long as you use the same volume on both sides. What we are looking for is the concentration of Fe3 plus once we have a solution of 10 milliliters. Okay, because when we add our 5 and 5, it becomes 10. So we do 0.2 times 5 over 10 equals our concentration of Fe3 plus. So that comes out to 0.1. So now we're going to do the same thing for SCN minus. So we start with this, and we use 5 milliliters of it. So what is our concentration when we have 10? So our concentration of SCN minus there, we do 0.2 times 5, 0.0002 times 5 over 10. So it's just like this one, except we're going to put our other concentration in there, and then that gives us this. So in this box, we will write 0.0001. And then we go to our table number 2. So we need to put this calculated number in table number 2 and process the data. So go down to table number 2 right here. In our reference concentration of FeSCN2 plus, we can put this. And the reason we can put that, you might notice, I just want to remind you, we didn't find the complex ion up there. We found the SCN minus, but because of Le Chatelier's principle and because we put so much of the Fe3 plus, we can just assume that all of that thiocyanate ion became the complex ion. That was the point of doing those two drastically different molarities for the reference solution. Okay, so that's why I can put that same concentration here. All right, so number 3, oh, you can see my pictures are a little off because when I download it into this app, sometimes it gets messed up, but your pictures will be fine. What might be helpful at this point is to pull up the lab on Classroom because I didn't have a color printer, so your paper copy is not going to have the colors that you would want to hear, okay? So you might want to pull up the colors on Classroom just to look at it. So the wavelength setting we will use in this lab is not chosen arbitrarily. The graph that you can see is the result of running a trial for which absorbance versus wavelength was measured. The graph of the data is shown below. So when I put this into the spectrophotometer, it gives me this graph, okay, absorbance versus wavelength. So the graph that you can see on your handout. It tells you that you should pick something between 0.1 and 1 for absorbance. So we're going to pick kind of like a really high peak here. What you can see is that the color of the complex ion is kind of, I mean, this color is a little off, honestly. You'll see that it's a lot more red. So if you look up at the top, that's the color we're going to see, like that color of kind of that FeSCN2 plus is going to have like that color red at the top. So it's like an orangey red color, okay? So if you look at the color wheel, if something is orangey red, it's going to absorb what's on the opposite end of the color wheel. Okay, so we're going to want something that is in that blue area, that orangey red, that blue area. So if you look at the bottom, that's going to tell us what we should set our wavelength at for the spectrophotometer. So right about that tallest peak is right about 450. Okay, and then if you look at the color wheel, that's right opposite our orange red that we're expecting our complex ion to be. If our complex ion, the color is orange red, right across from it is blue. That wavelength is right about 450. So that's why we set it for 450. Okay, so that kind of explains A and B. Okay, 550 is getting us over into that green, and that's not opposite the color that we want. Okay, that's opposite like a purplish red, and we're not going to be there. We're going to be at like an orangey red. Okay, so that kind of takes care of both A and B for the pre-lab. And then that's it. You can read through the procedure, get ready for our lab, but we will go through all the rest of this together.